to finish off that first example that we looked at with the alternating series test, we were looking at the second condition, which is that the limit of the function f of x, or in this case 1 over 2k plus 1, as k goes to infinity equals 0. And as you can see here, the denominator does go to infinity as the numerator stays constant at 1, so the limit is 0. The final conclusion that we make is that this is a convergent infinite series. The alternating series test allows us to make that conclusion because of these two conditions that this particular series did satisfy. Let's look at a second example. So we've got a different series that we're looking at this time, and that series is formed by taking -1 to the k plus 1 power, and that being our numerator, and our denominator being the square root of k. We're going to start with k equaling 1. So we could use the alternating series test because of the numerator causing the signs to alternate. So let's check each of the conditions to see if this converges. So the first condition will be to do the first derivative test to check to see if the function is going to decrease or be non-increasing after some value n. Sorry. What I want to do is I want to let f of x equal 1 over the square root of k, so leaving out the alternating sign, or writing that as k to the -1/2. If I take the first derivative of k to the -1/2, I'm going to get -1/2 times k to the -3/2. And so I can also write that as -1 over 2 times the square root of k cubed. There's our first derivative. Let's find the critical values by taking that first derivative and setting it equal to 0. We're looking for anything that makes the denominator undefined or the numerator equaling 0. And there's only one value that will do that. That's if k equals 0. That'll make the denominator undefined. So our capital N here is k equaling 0. The question is, for values larger than 0, is this going to be non-increasing? Or in other words, is it going to be decreasing? Let's choose a test value, anything bigger than 0. Let's go with 1. It's easy to plug in. So what I want to do is I want to take f prime and evaluate it at 1. You can see that what I'm going to get is a negative value, which is all I really care about. It doesn't really matter what the value is, but the fact that it's negative means that it's decreasing. So first condition is satisfied. It is going to be non-increasing, or in this case decreasing, for all values of k greater than 0. Second condition. What happens to the limit of the part of the function where the signs are not alternating as k goes to infinity? Well, in this case, the denominator, square root of k, is going to go to infinity, and 1 over infinity gives us 0. So it meets both of the conditions in the alternating series test, and by proving that and doing both of these pieces of calculus, we make a final conclusion that the infinite series that we were given, the infinite alternating series, converges. I have one final example for you of using the alternating series test. Here's my last example. Here we have the infinite series starting at 1, defined by -1 to the k times k over 3k plus 2. So what we're going to do in this case is form a function where we leave off the alternating sign piece. And we're going to check to see if it converges based on the alternating series test. So I know that the part where we have to confirm that the terms will be non-increasing after a certain point in the series, that sort of is a lot of work in that first derivative test. So if I have a hunch that it may not be, or even if I am not sure, I may start with the limit piece first, because that's quick and easy. And if that fails, then there's no need to even look at the other condition. So I already know, really quickly looking at this, that the limit is not going to be 0. And I know that because L'Hopital's rule will apply, and I'll get infinity over infinity, which means that I'll have to take the derivative of the top and the bottom, giving me 1/3. So since the derivative here is 1/3, it's not equaling 0, which was that criteria in place for the alternating series test to say that the series was going to the series was going to converge. But if we look at the divergence test instead, the divergence test says that if we take the limit of this k over 3k plus 2, and if it's non-zero, then our conclusion is that the series is divergent. So without redoing my limit, I'm going to get the same answer. I'm going to get this constant of 1/3 that does not equal 0. And therefore this series diverges. So this is what I was mentioning earlier in terms of the alternating series test and the divergence test being sort of a nice complement to one another, where the alternating series test will fail and not allow us to say that a series converges. The divergence test will pick up the pieces, and because we have a non-zero result, allow us to conclude that it diverges instead.